This is lesson 4-8, Driving Safety Data. Our quote is, "Nowhere in this country should we have laws that permit drinking and driving or drinking in vehicles that are on American highways. This is not rocket science. We know how to prevent this." This was a senator by the name of Byron Dorgan that said this. And it basically applies to any sort of distraction, whether it's impairment or whether it's just total distraction. This is not good and should be prevented in all cases. The objectives of this lesson are to calculate the reaction time and distance in the English Standard System, to calculate and use the braking distance in both the English Standard and metric systems, and to calculate and use the total stopping distance in both the English Standard and metric systems. So here are some key terms that we need to understand. Reaction time. This is the time it takes the driver to switch from the gas pedal to the brake pedal. Reaction distance. This is the distance that a car travels during the reaction time. Braking distance. This is the distance that a car travels after the brakes are applied. And then lastly, total stopping distance. This is the sum of the reaction distance plus the braking distance. So how can we use mathematics to become a safer driver? How long do you think it takes a driver to react to something in the roadway that requires the car to stop? When a driver applies brakes to a car, what factors affect how long it takes for the car to stop? And then lastly, what distance does a car travel before it stops? Well, first of all, in terms of driver reaction time, research shows that it takes anywhere from 0.75 to 1.5 seconds. So if you see something in the road, that's approximately how much time it takes you to take your foot off the gas and put a foot on the brake. Anywhere from 3/4 of a second to 1.5 seconds. Now, what factors affect how long it takes the car to stop? Well, it could be road conditions, for example, in the wintertime if the road is icy. And it could be condition of the car, specifically the brakes, how good the brakes are. And then lastly, what distance does the car travel before it stops? Well, if you're traveling at 55 miles an hour, a car travels approximately 80.67 feet in every second, okay? So if the reaction time is 1 second, during that 1 second, the car is going to have traveled 80 feet. And then however long it takes for the car to stop based on road conditions and the condition of the car, it's going to travel even further. So what are the results of speeding, tailgating, texting while driving, and driving while impaired? Well, let's take a look at this video.
Tailgating danger caught on tape. Keep your eye on these two cars. It's tailgating in the extreme, and it's about to get very serious. Suddenly, the motorist in the front hits the brakes. The tailgater completely loses control. The SUV plows off the highway in Wisconsin. Here it is in slow motion. First the brake check, then the slip and slide. Cops identified the tailgater as a 42-year-old woman. She was unhurt, but given a citation. YouTube videos show how frustrating dealing with a tailgater can be. Check out the pickup following close behind in this video. The truck driver overtakes and makes a rude hand gesture as he goes by, but then he loses control and runs off the road. This video was shot by a driver who's tailgating way too close. Suddenly, the car in front stops. This guy has apparently rigged his windshield washers to deal with tailgaters. Robert Sinclair of the AAA.
Robert, how dangerous was that tailgater in Wisconsin?
That tailgater was very dangerous. When you're on a highway in that situation, it's very difficult to deal with. It was impossible to pull over anywhere. There was no shoulder. So it made it very difficult for the driver that was being tailgated.
So, if you want to keep your cool, keep your distance.
Let's look at some examples. First of all, here's one example. What is the reaction distance for a car traveling approximately 48 miles per hour? So we're looking for reaction distance, okay? That's how long it takes, how far the car is going to travel when your foot moves from the gas pedal to the brake pedal. How far has it traveled in that period of time? Well, whenever we're converting, okay, basically what we need to do here is we need to convert miles per hour to feet per second, all right? So this is what we need to worry about here. Now, whenever I'm doing a conversion like this, I look at units, all right? So we start with miles per hour and we want to end up with feet per second. So miles per hour times hours per minute, the hours are going to cancel, times minutes per second, the minutes are going to cancel, and the miles, which is over here, and over here, what are we going to be left with? We're going to be left with feet per second, okay? So at 48 miles per hour, there's 1 hour per 60 minutes, 1 minute per 60 seconds, and 5,280 feet per mile. That means we travel at that speed, we go 70.4 feet every second. So at 48 miles per hour, we travel 70.4 feet every second. Now, if we assume a reaction time of 0.75 seconds, which is pretty quick, that means as a minimum, we're going to travel 52.8 feet, because we simply multiply the feet per second times 0.75 seconds, and we come out with 52.8 feet. Now, we don't typically do this calculation every single time we are concerned with reaction time and braking time. There is a conservative rule of thumb, okay, that is used quite often. And this rule of thumb is that the car travels 1 foot for each mile per hour, okay? So if it's going 10 miles per hour, it's going to travel 1 foot, okay? Reaction time is going to be about 1 foot, all right? 1 foot per second. Here's another example. What is the approximate braking distance for a car traveling at 48 miles per hour? We got reaction distance, and we said the rule of thumb is about 1 foot per mile per hour. That's how far the reaction distance is going to be. So what is the approximate braking distance for a car at 48 miles per hour? Well, there is a basic formula for this, and this is braking distance is equal to the speed squared divided by 20. All right, braking distance is in terms of feet, speed is in terms of miles per hour, and you divide it by 20. So therefore, at 48 miles per hour, the braking distance would be 48 squared divided by 20, or 115.2 feet. So at 48 miles per hour, the braking distance for a car, now this is typical, okay, that it could vary depending on the condition of the car and the conditions of the roads, but typically the braking distance using this formula would come out to be 115.2 feet at 48 miles per hour. All right, here's another example. Rachel is driving at 48 miles per hour on a one-lane highway. She sees an accident directly ahead of her about 200 feet away. Will she be able to stop in time? Well, let's do some calculations and see whether she can stop in time. Now, as you'll recall, the total stopping distance is equal to the reaction distance, how far the car travels when she's reacting, moving her foot, and the braking distance, okay? And we previously calculated these. So the total stopping distance, using our rule of thumb, 48 miles per hour is going to be 48 feet, okay, that the car will travel during the reaction distance. And we previously calculated the braking distance based on 48 miles per hour is typically going to be 115.2 feet. So therefore, this comes out to the total stopping distance is 163.2 feet. Well, this is less than 200, so yes, she will be able to stop in time because it's going to take her 163 feet to stop the car, and she's 200 feet away from the accident. Okay, let's look at another example. Here, Desiree is traveling through Canada. As you recall, Canada is under the metric system. In fact, the speedometer on her rented car indicates kilometers per hour, and all the road signs give distances in kilometers. She knows that 1 kilometer is equal to 1,000 meters, and 1 meter is a little more than 3 feet. Let's determine Desiree's total stopping distance if she is traveling 88 kilometers per hour. First of all, we can do this a number of different ways. Let's start off by converting 88 kilometers per hour to miles per hour. Now, the conversion between kilometers and miles is about 0.621371. So if I multiply 88 times that, I come out with the equivalent miles per hour speed of 54.68 miles per hour. So 88 kilometers per hour equals 54.68 miles per hour, approximately. Now again, remember, total stopping distance equals reaction distance plus braking distance. All right. Now, remember our rule of thumb for reaction distance is going to be 54.68 feet if it's 54.68 miles per hour. And remember, braking distance typically is going to be the speed squared divided by 20. So 54.68 squared divided by 20, which comes out to be approximately 204 feet, or if I convert that to meters, it comes out to be 62.23 meters, okay? So that's her total stopping distance. Now, I can always do that formula, but if I prefer, there is a quicker way to do it, and that is the total stopping distance in meters. Okay, the total stopping distance in meters is equal to s squared over 170 plus s over 5, where s is in kilometers per hour, and the total stopping distance comes out to be in meters. So if I plug in her speed, which was 88 kilometers per hour for s, so I've got 88 squared over 170 plus 88 over 5, we come out with approximately 63.15 meters, which, if we compare it to our other method, is pretty close to being the same thing, okay? But it certainly is a lot quicker to use this formula than it is to take and do all the conversions necessary for everything else. So hopefully you've learned a little bit about driving safety and so that you can avoid accidents when you're driving in the future.